Material from section 1.7 where we learned about inverse functions in OpenStax PreCalculus. Basically what's going on here is it's a really challenging problem, but this specific problem I like because it illustrates so many different concepts and different ideas that have to do with this section that maybe it cements your knowledge for the rest of the problems, that even if you don't see problems quite this hard. So at any rate, the problem says here's a function, f of x equals 2x squared minus 8x plus 4, and you're asked to find f inverse of x. There's a problem that's impossible, which is unfortunate. So I guess if you were given this question, you could just say, no, I'm not going to do that. I can't do that. It's impossible. Why is it impossible? Well, it's because this function right here is not one-to-one, right? This function, f of x equals 2x squared minus 8x plus 4, is not a one-to-one function. You know that either because it's a second-degree polynomial and you kind of have an idea about what those graphs look like, or because you took the time to graph this thing, and your graph looks something like this, 2x squared minus 8x plus 4. And this graph right here would not pass the horizontal line test. Right, there's a horizontal line right there that crosses my graph in more than one spot, which is okay. That doesn't mean it's not a function. It just means it's not a one-to-one function, which means that I cannot define its inverse. So then what the hell am I going for here? Okay, so what we're going to do here is we're going to make this problem, we're going to make this function one-to-one so that we can find its inverse. And the way we're going to do that is, if you notice the vertex right here is at 2, -4, this little dot. If I restrict the domain of this function to all x values that are greater than or equal to 2, essentially what that does is it makes this function one-to-one. So what I'm saying is I got this graph right here, this parabola, but if I only allow people to put x coordinates that are 2 or larger into this function, well, let's see, you could put in 2 and -4 comes out, and then you can kind of, I guess you could trace this thing and follow through to get some more points on here. Or you could just figure out what comes out when I put 4 in. Oh, it looks like 4 comes out. At any rate, you could find some other points that are on this graph. Here's another one. It turns out that -2, 3 is on this graph. Don't believe me? You can just type in -2 here and whoa. Sorry, 3, -2. You could type in 3 and -2 would come out. 3 is the input, -2 is the output. So you connect these as best you can with this U-shaped graph for my parabola. And that's not too bad. You end up with something like this as your graph. And the advantage of this, as opposed to this entire parabola, is by restricting the domain like I did here, I come up with the graph that's one-to-one. And having a graph that's one-to-one is fantastic because then I can find the inverse function. That's what I'm going to be doing through this example. Before I worry about that algebraically, I want you to realize that you could come up with a graph of the inverse function. Right? If the function goes through the point 2, -4, then the inverse function goes through the point -4, 2. This point right here. And the function goes through 3, -2, so -2, 3 must be on the inverse function. And 4, 4 is on the function, so 4, 4 is on the inverse function. Essentially what I'm doing is I'm taking all of the points on the graph in red and reflecting them over the line y equals x to come up with a graph that looks something like this. This is f inverse of x. If this looks like transformations of the toolkit function f of x equals the square root of x, that's good because that's exactly what it is, as we'll see when we do this thing algebraically. So okay, let's put this on hold for a little while. Let's go back up here. I have this function. I want to find its inverse. Yes, I restricted the domain, but you can kind of ignore that for a little while. It will come into play algebraically. I'll let you know when it does. But for now, just kind of start out at it naively. Wait, inverse function, that's the one where I change the f of x into a y? And what that gives me is an equation that represents the function. And what I can do is I can change all the y's to x's in this equation and all the x's into y's. And what that will do is give me an equation that represents the inverse function. Because the inverse function and the function are very similar. The only difference is I switch the inputs and the outputs. But this is an equation that represents the inverse function. It's not written in function notation. To write it in function notation, I got to solve for y. That's going to be hard. That's going to be really hard, actually, because I have a y here and a y here. And worse yet, this y is squared, and this y is just a y. It's to the first power. That's going to be really challenging to solve for y. In fact, there's a method, a trick for how to solve for y here that you may or may not have seen in a previous class. It's called completing the square. It's a really useful algebraic topic, so I'm going to talk through it right now. The way I think of completing the square is you can only do it when on one side of the equation you have your y squared, or your squared term and your linear term. So your variable squared and your variable, and nothing else. And furthermore, the coefficient on your variable squared has to be 1. So what I'm saying is I don't want this 4 here. Okay, just subtract it to the other side, no problem. X minus 4 equals 2y squared minus 8y. Now I have my y squared term and my y term on the same side of the equation, but my leading coefficient here is not a 1. But I can make it a 1. Divide everything by 2. I got x minus 4 divided by 2 equals y squared minus 4y. Now I can complete the square. And the way you complete the square is you make the right-hand side of the equation a perfect square. And the way you make it a perfect square, well, I'll do it and then I'll explain how I do it. Yeah, I guess I can write another line. So I got on the left side this x minus 4 over 2 thing. And then on the right side I got y squared minus 4y. And unfortunately, y squared minus 4y is not a perfect square. There's nothing that when I square it will give me y squared minus 4y. But if I had a plus 4 at the end right here, I would have a perfect square. I can't just go throwing a plus 4 here unless I add 4 to both sides of the equation. So for some reason I chose to add 4 to both sides of the equation, and I realize you might struggle with why I did that, but at least you can see how I did it. Add 4 to both sides, no problem. And then it turns out that on the right side I got y minus 2 squared. I have a perfect square. And you're like, wait, hold on, slow down. Several questions. First off, y plus 4, how'd you know that? And then secondly, how do you know that this equals this? I can answer those questions in a couple ways. The first way is I can say, well, FOIL this out, try it. Figure out what y minus 2 times y minus 2 is. I bet you get this. Okay, so I can check my answer, but how would I find my answer if you, me, weren't here talking through this? Well, the trick to it is to make this line a perfect square. The thing that you add, so let me write some stuff in here. This negative 4 right here tells me that b is equal to negative 4. And what I'm going to write right here will always be half of b squared. So I decided b was negative 4, and this would still work if b were negative 8 or negative 7 or negative 5 or negative 3 halves, whatever. That's fine. b is some number. And then cut it in half. Half of negative 4 is negative 2, and then square it. Negative 2 squared is positive 4. This being a 4 and this being a negative 4, it's a coincidence here. It's because half of this number squared is also 4. But these won't always be the same value. You're always going to add that to both sides of the equation when you're completing the square. And that will always give you a perfect square on the right-hand side of this equation. Oh yeah, I guess I see that y minus 2 squared is this thing, but what if I don't? What if I don't recognize that? Well, there's good news. This will always be y, let's see, plus b over 2 squared. Wait, you wrote y minus. No, I didn't, because b is negative 4. So b over 2 is negative 2. So y plus negative 2 is what I wrote right here. Just instead of writing plus negative 2, the standard is to just write minus 2. So I got y minus 2 squared. Going from this line to this line is called completing the square. And it's a very useful algebraic trick that you may not have known. But it ends up being what you need to solve this problem. Because remember, go back. Wait, I just learned this new concept. I forgot what the hell I was doing. Remember way back up here when we changed the y's into x's and the x's into y's? Our goal was to solve for y. But that was a challenging goal because we had multiple y's, this y squared and this y. Look where we are now. We only got a single y. That's fantastic. Instead of having a y squared and a y, I just have the letter y written one time. I could solve for that. I could isolate this y right here. No problem. Get rid of the square root, get rid of the negative 2, you got the y all by itself. I take the square root of both sides of the equation, and you got x minus 4 divided by 2 plus 4. The square root of that equals y minus 2. You might be yelling at your computer screen and be like, hey, dummy, anytime you take the square root of both sides of an equation, you got to put in a plus or minus. You're right, but you're kind of wrong. It's true that anytime you take the square root of both sides of an equation, you should put in a plus or minus. However, the reason I'm not going to put a plus or minus right here is because if I put in a plus or minus, when I solved for y, I would not have a function. Right? I would have 2 plus or minus this thing, and I can't have a plus or minus because then when I put in one input, 2 outputs come out. And that can't happen for a function. And now you're kind of thinking, oh, right, the one-to-one thing and a function. What's going on here is I don't have to put a plus or minus right here because I restricted the domain. Or because I restricted the domain of the function to only include x values that are greater than or equal to 2, I'm restricting the range of the inverse function to only include x values that are greater than or equal to 2. And by not putting in the plus or minus right here, I keep the range consistent with what it should be. What I'm saying is just forget about putting the plus or minus here, and you'll always be able to forget about doing that. I'll come back to that and talk about it a little more in just a second, but first I want to finish this problem. This right here is my function. It's not the prettiest thing in the world, so maybe you would choose to clean it up, or maybe you wouldn't. I don't know you. You could make this 1/2 x, and because you could make this x over 2 minus 4 over 2. But 4 over 2 is 2, so it's really x over 2 minus 2 plus 4. But minus 2 plus 4 will just look like this. I think this is prettier than this, but it's kind of subjective. Beauty is in the eye of the beholder. I like this form of my function. And the reason I like this form of my function is it's easier to see the function transformations. Right? This is just function transformations of the square root of x. It looks like I multiply the x value by 1/2, I add 2 to the x value, and I add 2 to the y value. So if you think about what that does in terms of the transformations, this is what I divide all of my x coordinates by. So I'm going to divide all of my x coordinates by 1/2, aka multiplying by 2. And this is what I subtract from all of my x coordinates. So I'm going to subtract 2 from all of my x coordinates. And then I'm going to add 2 to all of my y coordinates. So picture, I'm not going to draw it here, but picture your toolkit function, the square root of x, that looks something like this. I am going to first move everything to the left by 2. So now it kind of looks something like this. And then I'm going to divide all of the x coordinates by 1/2, but dividing the x coordinates by 1/2 is the same as multiplying the x coordinates by 2. So the geometric effect that it's going to have is going to kind of stretch things horizontally. Instead of looking like this, it's going to look like this. Almost the graph in green, just 2 units below it. But this 2 right here is going to shift everything up. It'll get me to this graph in green right here. So this right here is the inverse function. It's what I graphed in green right here. Maybe I should have done it in green so that it would color code a little bit nicer. A comment, us leaving off the plus or minus right here and just taking the positive square root. That came because we just took the positive side of this parabola right here. You can almost see that if you had kept the negative side of this parabola, and this might be a bad idea to draw this in here, it might make the picture harder to look at, but I've gone this far. And you were going to reflect over this graph, what it would have looked like, roughly speaking, is something like this. This is not a function, right? It doesn't pass the vertical line test. If my function is not 1-to-1, then my inverse does not become a function. Doesn't pass the vertical line test when the thing in red doesn't pass the horizontal line test. So I restrict the domain of the red. I erase this stuff in the dotted line right here. And what that does is erases this stuff in green right here. Had I erased the right side and kept the left side, by the way, people never do. The standard is to keep the positive side of your domain. But I suppose you could have said x has to be less than or equal to 2, and you'd end up with a 1-to-1 function. This would have been gone, and this would be here. Then algebraically, when I was solving, and I should have put a plus or minus right here, I would have left the minus and not kept the plus. And my graph would have looked like this instead. But nobody ever does that. You always keep the positive side of the parabola. You always keep this side, which makes the inverse function this top half here, which is nice because when people are solving this, more often than not, they forget to put in the plus or minus to begin with. And by screwing that up, by forgetting to put in the plus or minus, they actually do the right thing because you don't want the plus or minus, you only want the positive solution. At any rate, this is the inverse function for this crazy function right here. In fact, you could check your answer. You could check your answer a lot of different ways. I'm going to show you a couple. I could take this as a function and find its inverse. The inverse of this function should be this thing right here. Let's see if it works. Make this a y equals 2 plus the square root of 1/2 x plus 2. So subtract 2 from both sides. Square both sides of the equation. You might be tempted to subtract 2 and multiply by 2, but if you do that, you won't get something that looks like this unless you get rid of these parentheses. So I'm going to go ahead and FOIL this out right now. You could FOIL it at any point. I get y squared minus 4y plus 4. Hey, wait a minute. It's almost like I'm doing these steps backwards. Right? This stuff kind of look familiar. The y minus 2 squared, the y squared minus 4y. Really, a lot of this, what I'm doing is just undoing what I did before. At any rate, that equals 1/2 x plus 2. So then subtract 2 from both sides. You got y squared minus 4y plus 2 equals 1/2 x. Multiply both sides by 2. Really, shoot, I should be consistent. Before I did any of this, if I want to follow up in this line, I should have changed all my y's into x's and x's into y's. So I'm going to do that. I'm going to make this an x. This is ugly. And make this a y. And therefore this is a y. And this is an x. And this is an x. And this is an x. And that's an x, even if it doesn't look like it, trust me. And then this is a y right here. Because really I'm solving for y. And I'm going to multiply both sides by 2 to get y all by itself and get y equals 2x squared minus 8x plus 4. Drum roll. Hey, right what I started out with. Cool. Yeah, the inverse of the inverse should be the function. That's kind of a neat little check. There's more ways you can check this. You can compose these guys together. You can find, I don't know, maybe f of f inverse of x. That better be equal to x. If this really is the inverse, when I compose it with the function, in either direction, it should be equal to x. Well, can you do that? F inverse of x, we figured out down here, was 2 plus the square root of 1/2 x plus 2. And so since I have this blueprint for f of x, I can copy this, except everywhere I see the letter x, I instead write all this stuff. So I got 2 times, and then instead of writing the letter x, I'm going to write 2 plus the square root of 1/2 x plus 2 squared. 2x squared minus 8x, but instead of writing x, I'm going to write all that stuff that was in the parentheses, plus 4. And when you simplify this mess out, we better get x as our answer. Let's see if that happens. I guess you could FOIL this whole thing out. I'm not thrilled about it, but I'll do it. If you took this thing and multiplied it by this thing, the 2 times the 2 would give you 4. The 2 times the square root of 1/2 x plus 2 would be 2 of these square root of 1/2 x plus 2's, but you're going to get 2 of those things because the O and the I in FOIL will be the exact same. You're going to get 4 square root of 1/2 x plus 2. And then the L in FOIL, this times this, well, the square root of something times the square root of that same thing would just be 1/2 x plus 2. That's this thing squared. So I got 2 times that minus 8 times 2 plus the square root of 1/2 x plus 2 plus 4. Pretty high level algebra going on here, but I'll continue. I'd like to combine like terms. Maybe take this 2 and distribute it through, and take this -8 and distribute it through. If I take the 2 and distribute it through, I get 8 plus 8 of these square root of 1/2 x plus 2 things. 2 times 1/2 x would just be x. 2 times 2 would be 4. And I took this 2 and distributed it to all 4 terms in these parentheses. And then take this -8 and distribute it through. -8 times 2 is -16. -8 times the square root of 1/2 x plus 2 is -8 times the square root of 1/2 x plus 2. And then you got this plus 4 here. What a mess. Actually, it's not, because this term and this term cancel out. So I got 8 plus 4 more is 12. Plus 4 more is 16 minus 16. That all cancels out too. All that survives is this x right here. Fantastic. F of f inverse of x really was x. That's a nice little check. I'm not going to do it. Yeah, I'll do it. Why not? We could also figure out f inverse of f of x. Same basic idea. Just now the input is f of x, which was given to me to be 2x squared minus 8x plus 4. So what I can do is I can take this f inverse and use this as my blueprint, and everywhere I see the letter x, change it into this thing. So I would have 2 plus the square root of 1/2 times, and then instead of writing x, I'm going to write all this stuff. 2x squared minus 8x plus 4. Plus this 2. Some function composition practice here. Well, let's see how this works out. I guess I could get rid of these parentheses here. I could take this 1/2 and distribute it through. This is a 4, even if it doesn't look like it. Take the 1/2 and distribute it through. You get the square root of 1/2 times 2x squared is just x squared. 1/2 times -8x is -4x. 1/2 times 4 is 2. And then you have this 2 also. So really what you get is 2 plus the square root of x squared minus 4x plus 4. wait, isn't this supposed to be equal to x? I'm composing a function and its inverse. If I did things right, this should be equal to x. It's hard for me to see how this is equal to x. It is. See it? Is this thing inside the parentheses, is this perfect square? All right, this thing, not inside the parentheses, sorry, underneath the radical, is a perfect square. Underneath the square root sign, I have x minus 2 squared. X minus 2 squared is x squared minus 4x plus 4. And this square root and this square kind of cancel each other out. That's a bit of cheating. Really, I should put absolute value signs here when I have a squared nested inside of a square root. But I don't need to put the absolute value symbols in here. And where that goes back to is this idea of restricting the domain. Since x is greater than or equal to 2, this thing, if I had absolute value symbols right here, but if x were always greater than or equal to 2, that thing inside the absolute value symbols would always be positive. I'm going to write it. Absolute value symbols, but because of my restricted domain, that just equals this. And 2 minus 2 cancels each other out. I get x. I'm thrilled. Another check that I didn't have to do, but I just figured this was a hell of a lot of practice with some pretty complicated function composition. We got into function transformations with the graphs here. We did all sorts of stuff on inverse functions. Learned this cool technique for completing the square. So I just wanted to make sure people saw this example just because I think it has so many different skills in it. I'll end this video here.